Hello students, welcome back. In this part, we'll discuss more about the structures of some other ionic compounds. So let's start. Now we are going to discuss about the structures of some other ionic compounds which are important for us. One is A to B type, or Li2O is one of the example of A to B type. So let's understand the structure of lithium oxide in detail. So this Li2O lithium oxide has an arrangement of cations and anions opposite to the fluoride structure. So the structure calcium fluoride or Ab2 type is known as fluoride type structure. Ab2 is known as fluoride structure. So this has an arrangement of cations and anions in exactly opposite of the fluoride structure. So that's why this structure is known as anti-fluoride structure. Okay, it is known as anti-fluoride structure. Yeah, you can see in this image the dilithium oxide. In Li2O, in dilithium oxide, the oxide ions constitute the cubical close packed structure, and the lithium ions will occupy all the tetrahedral voids. Okay. So in CaF2, if you recall, in calcium fluoride ions are occupying all the tetrahedral voids. Anions are occupying all the tetrahedral voids in calcium fluoride. But whereas in lithium oxide, Li2O, the cations are occupying all the tetrahedral voids. So here the arrangement of cations and anions is exactly opposite of fluoride structure. So that's why this type of structure is known as anti-fluoride structure. So oxide ions are occupying the FCC structure, that is the red ones are oxide ions which are present at all the corners as well as the face centers, and the lithium ions are occupying all the tetrahedral voids or tetrahedral holes. Okay. So each oxide ion is in contact with 8 lithium ions. So if you take each oxide ion which is in contact with 8 lithium ions, and each lithium ion that is occupying the tetrahedral site is only contact with the 4 oxide ions. So that's why the oxide ion coordination number is 8, the lithium ion coordination number is 4, and therefore Li2O has 4:8 coordination. That is, coordination number of lithium is 4 and the coordination number of oxide is 8. It is having 4:8 coordination. And some other examples of anti-fluoride structure are sodium oxide, potassium oxide, potassium sulfide, rubidium sulfide, etc. So all these are anti-fluoride structure. So next is A2O3 type structure, that is corundum type structure, and one of the example is Al2O3, that is aluminum oxide, is having a corundum structure. So let's understand about the structure. So the general formula of the compounds crystallizing in corundum structure is A2O3, where A is any type of ion, A is an cation and this is oxygen, so which is having a general formula A2O3. So if A is aluminum, then Al2O3 will be the one example. So in this corundum structure, anions are occupying the hexagonal primitive lattice. That is, anions, those are oxide ions, are HCP arrangement. They arranged hexagonal close packed. And if you take the cations, like example, if I take aluminum Al plus 3, it is occupying only 2/3 of octahedral voids. Okay, only 2/3. So we know that in HCP there will be six atoms, right? So since there will be 6 atoms, so octahedral sites or octahedral voids will be 6. So it will be 2 by 3 into octahedral sites are also equals 6, so which comes to be 4. Okay, so there will be 4 aluminum ions and there will be 6 oxygen, 6 oxide ions. So it will be, if you simplify, it will become Al2O3. So that is the one of the example of the corundum structure. Okay, so what you need to remember here is the anions are arranged in hexagonal primitive lattice, and the 2/3 of the voids, 2/3 of the octahedral voids are filled with the trivalent cations. So some of the examples of A2O3 type structure is Fe2O3, Al2O3, Cr2O3, which are having corundum structure. Okay, so for each and every structure, write down clearly how the cations are arranged and how the anions are arranged. So next is perovskite structure. So perovskite is having a general formula AbO3. It is having a formula AbO3 where one of the cation, so oxide ion is the anion, so A and B both are cations, so one of them is bivalent, another is tetravalent. So A is going to be trivalent and B is going to be tetravalent. Okay, so one of the cation is bivalent and other is tetravalent. Example is BaTiO3 or CaTiO3 is example that you can consider, that is BaTiO3, the barium is +2, the titanium is +4. So here the bivalent ions are present in primitive cubic lattice. They are present in primitive cubic lattice, that is a simple cubic, and the oxide ions are present at the center of each phase. So where you can see, this is in this example BaTiO3, where the bivalent ions, what are the bivalent ions? Barium ions, right? So the barium ions which are shown in yellow color are present at the corners, right? At the corners, and the oxide ions which are anions are present at the centers of all 6 faces. So which are shown in blue color, the blue color particles are oxide ions. So there are 6 faces, so there will be 6 oxide ions at the center of each phase. Okay, so we have one bivalent ion position we know, and one and the anion position we know, and next is the tetravalent cation. So here it is Ti+4. Tetravalent cation is in the center of the unit cell occupying the octahedral void. So here the red one is the titanium, which is tetravalent and which is there at the center of the unit cell occupying the octahedral void or octahedral site. Okay, so Ba+2 barium ions are at the corners, so simple cubic. So simple cubic means there will be only one barium ion, and the Ti4 ion is present at the center. So at the center only one titanium ion is there. Oxide ions are present at the center of the 6 faces. So it will be 6 into 1/2, that will be 3. So there will be one bivalent ion, that is Ba+2, and one tetravalent ion, and there will be three oxide ions. So the formula will become BaTiO3. Okay, so here in the picture the coordination numbers are also you can get. So the bigger one A is a what? A is the titanium ion or the tetravalent ion. So which is, yeah, these are the oxide ions. So its coordination number is 6. Okay, and if you see yeah, and one more thing, oxide ion is having also a 6 coordination number. So one titanium above, below, and there will be 4 barium ions. Okay, so this is about the AbO3 type structure, which is perovskite structure And let's go to the last type of structure, that is spinel structure. Spinel structure. So spinel is a mineral which is MgAl2O4. So generally they can be represented by this formula. So which is this is bivalent and this is tetravalent and this is oxide. Okay. And here we have to know the positioning of them, positioning of ions, positioning of cations as well as anions, where the M+2 ions are present in 1/8 of the tetrahedral voids in FCC lattice of oxide ions. So oxide ions are forming FCC lattice. So write down here the oxide ions are forming FCC lattice, and the M+2 ions, in this case that is magnesium ion, is present in 1/8 of tetrahedral voids, 1/8 of tetrahedral voids, and the M+3 ions are present in half of the octahedral voids. So M+3 ion, that is the trivalent ions, are present in half of the octahedral voids, half of the octahedral voids. Okay. So here the bivalent ion is magnesium, iron, cobalt, nickel, etc. And the trivalent ion is, it may be aluminium, it may be iron, it may be manganese, chromium, etc. So the examples of the spinal structure is ZnAl2O4, FeCr2O4. Okay. So you can get the formula, you can count the number of oxide ions. So oxide ions are occupying FCC, right? So there will be 4 oxide ions, and so there are 4. Since it is FCC, the tetrahedral voids will be 8, right? So 1/8 into 8, that will be 1. So 1 M+2, and there will be 4 octahedral voids. So 1/2 into 4, that is equals to 2. Okay. So there will be 2 trivalent ions, 1 bivalent ion, 4 oxide ions. So this is about the spinal structure. Okay. So this is all about the structure of some ionic compounds which are very, very important for us. So let's solve some MCQs based upon the concept that we learned till now in this part. Okay. The silver iodide crystallizes in a zinc blende structure with iodide ions forming the lattice. Then calculate the fraction of the tetrahedral voids occupied by the silver ions. Okay. The options are 50%, 75%, 25% and 35%. So how we can solve this question? So first understand what is given in the question. So which is silver iodide is AgI, crystallized in a zinc blende structure with the iodide ions are forming the lattice. Okay. So let's say suppose that it is having the lattice formed by AgI, silver iodide is having N Ag plus ions and N iodide ions. Okay. So N iodide ions are forming the lattice. Okay. So calculate the fraction of tetrahedral voids occupied by the silver ions. So if the lattice is formed by N number of iodide ions, so there will be 2n number of tetrahedral voids, right? Double the number of the close packed ions. So there will be 2n number of tetrahedral voids, but only we have n number of silver ions. So out of 2n, only n are occupied by silver ions. So it will be 1/2. That is only 50% of the tetrahedral voids are occupied by silver ions. Okay. So that is what happens in zinc blende. The cations will only occupy the 50% of the all tetrahedral voids available. So 50% will be the answer. So A will be the correct answer. So let's go to the second question. The cesium chloride has PCC structure with the cesium with Cs plus at the center and chloride ion at each corner. So the radius of anion as radius of cation as well as anion is given. So what is the edge length of the cube? Okay. So here before in the structure of cesium chloride I have given you a formula. So that is radius of cesium plus radius of chloride is equals to what? It is √3a/2. So this is given 1.69 plus 1.81 is equals to √3a/2. So here we need to find A, so you can easily find out. So which is how much? 916. It will be 3.5 into 2 divided by root 3 will be our edge length. So it is A is equals to 7 by root 3. So this value comes around 4.04 angstrom. So the answer is C, which is 4.04 angstrom, which is the edge length of the cube. Okay, so this question you can easily do if you know this particular formula, right, that we got from the structure of cesium chloride. So let's go to the next question. The two ions A plus B are having a radii of 88 and 200 picometers respectively. In the close packed structure of the compound AB, predict the coordination number of the cation, which is equals to A plus. Okay, so here we have to predict the coordination number of the cation, which is A plus. So let's see the options: 3, 4, 6 and 12. 3, 4, 6 and 12. So which is the correct one? So to know the coordination number, you can solve it. Just find the radius of A plus by radius of B minus. So which is 88 by 200. So if you solve it, you will get how much? 244 200s. So it will be 0.44, right? So this radius ratio, radius of cation by anion, it fall in the range of 0.414 to 0.732, right? Okay, so if the radius ratio fall in this range, the coordination number will be what? It will be 6. So C will be the correct option. So 6 is the coordination number of the cation A plus. Okay. So students, in this part we discussed about the structures of some other ionic compounds. We discussed about the structure of type A to B, and then we discussed about the structure of corundum, and then we went on to discussing the perovskite structure, and we finally learned about the spinel structure. So these are all some very important ionic compounds structures which are important for JEE purpose. And now, can we have an ideally perfect crystal in our real life? If not, then what are all the imperfections or defects can present within a crystal? So to know more about the defects present in a crystal, keep watching for my next part.